Hello, fellow weather enthusiasts. My name is Christopher Caparelli.
And my name is Nicholas Servidis, and today we will enlighten on the process of baroclinicity via a simple homemade experiment.
Before we demonstrate the process of baroclinicity through our experiment, Nick will first give a brief explanation on this topic.
So let's talk about baroclinicity here. So what is baroclinic instability? It can be simply thought of as an atmosphere where different air mass regions exist. Why do these different air mass regions exist? Well, it's relatively simple, all due to the planet Earth's axial tilt of 23.5 degrees. Now, this tilt controls the amount of solar radiation striking the Earth's surface. For this reason alone, higher latitudes, as illustrated here, actually see less solar radiation per area compared to the lower latitudes where there is more solar radiation directed per square area. Now, for this reason alone, solar radiation is actually proportional to temperature, and therefore, where we have more direct solar radiation, we have our higher temperatures. Where there's less direct solar radiation, such as the polar regions, cooler temperatures. Therefore, baroclinicity. But however, the reason this baroclinicity is so important is because these different temperatures actually make weather. That's why we get storms, low pressure systems, cold fronts, warm fronts, you name it, baroclinicity, principle behind it all.
Thank you for the explanation on baroclinicity, Nick. We will now give an illustration to show a small-scale example of baroclinicity at work. In this example, we created a smaller version of the Earth's atmosphere. Within this plastic container, you can see two different liquids. The liquid on the left is vegetable oil, which has a density coefficient of 0.93 grams per centimeters cubed. The liquid is representative of warm, less dense air. On the right side of the container, we have a purple-dyed water, which has a density coefficient of 1 gram per centimeter cubed. This liquid represents cold, dense air in the atmosphere. Recall that density is proportional to temperature. Therefore, the higher the temperature, the lower the density, and vice versa for cooler air. At the beginning of our experiment, we separated these air masses with a folder along with dough to create an impermeable barrier. As these two liquids sit, all of their energy is tied into potential energy. Once we remove the folder, Nick and I will illustrate that the potential energy of these two liquids will be converted into kinetic energy, with the more dense liquid subsiding due to a greater transfer of potential to kinetic energy and the less dense liquid rising over it. Based off of what we've learned thus far about baroclinicity, let's see if our experiment holds true to illustrate the behavior of interacting warm and cold air masses based off their densities. Shall we, Nick?
Let's hit it. So, that was a great experiment, Chris.
That was pretty cool, man.
I think the class will enjoy it.
The class will enjoy it. That was pretty sweet.
So, our demonstration accurately depicts what we observe in the real atmosphere. Let's think of a weather event that forecasters and even people alike look for. Cold fronts. What is a cold front? It's simply a large-scale weather system that abides by the same principles as seen as in our experiment. The severity of our weather is dependent upon the gradient of temperature over a small area. The stronger the temperature gradient, Chris, the more severe the weather event. And this can be understood by the energy conversion processes. When a very cold air mass moves into a region with a very warm existing air mass, an immense amount of potential energy will be converted to kinetic energy for the cold air to subside beneath the warm air. This subsidence will force the warm air to ascend and thus producing clouds and precipitation. Now, remember the behavior of the water in the experiment? It went down exactly too. In these simple processes, that ultimately give us the mechanisms for cooler and warmer days and rainy ones. All in all, baroclinicity is always playing a role in our day-to-day weather observations.
Awesome, Nick. Awesome. Thank you for that explanation.
You're welcome.
All right. So this concludes our weather lesson on baroclinicity. We hope you enjoyed our presentation. We look forward to speaking with you all soon. Have
Go
a great
Pack.
day. Go Pack. That was good. Go Pack was good at the end. I like that.